Hey guys, today we're going to be going over Module 4, Chapter 11, Transformations, Symmetries, and Tilings. My name is Katie Hardister, and we can jump on in. So for our first question that we have, the students were asked to horizontally flip the original shape. And so what our question is what degree did they flip the shape? So we see the original image here on our left-hand side, and let's watch the students as they flip the shape. So the students have flipped the shape, and at this point, we're wondering, well, did they actually, of course, flip it horizontally? And if not, then what degree did they flip the shape? So I would say that they did not flip the shape horizontally. And I would say that they flipped this 180 degrees. The reason that I say that is because we started here at the top and we watched it go all the way, forming almost what looks like is a half circle. And if we think about a circle, and that is not a very good circle, but we know that a circle is 360 degrees to make a full circle. So if my shape only went halfway, then that means that 360 divided in half or by 2 is 180 degrees. So I know that the students only flipped the shape 180 degrees. So, but that still doesn't answer my question. So if we're wanting to horizontally flip, so whenever I hear the word horizontally flip, what I think of is a reflection. So let's say that, we're given the shape, okay? And so we can see our little guy down here in the corner. And so that reflection, when I think reflection, I think of a mirror. So I want to take my shape and I want to draw a dotted line, and that dotted line is going to be my mirror. So if I was in an actual classroom, something that we could do with our students is give them little mirrors, and we could give them shapes or have them make their own shapes and put them in the mirror. And if I was to put this shape in the mirror, then I would see, of course, the horizontal flip. So I just took the shape and I crossed it over. This would be our x-axis. So I could also do, a vertical flip. So anytime that you're doing it, and I guess I kind of, for this equation, I flipped it the other way. So this would be what's called, I guess it still would be a horizontal flip, but you could do it vertically or horizontally. So if it was vertically, it would just be the other way, flipped across the other axis. So jumping into the next. So now that we've kind of covered, of course, our flipping and, our rigid motions, now we can look at what's called line of symmetry. So a line of symmetry is any time that we take a shape, if I can fold that shape in half at any of its corners and I still have the same shape, then it's going to be, it's going to have a line of symmetry. So we're taking a look at our first one here, and I see that I draw the line here down the middle. So we start at the top and we draw our line. We're going to fold it right down the middle. Okay. So if we were in class, then I would have my students, of course, cut out these shapes and we would fold the shapes in half, and they could make their own shapes. We'd start off with kind of more of our basic, like our circles and things like that. Those are kind of easy ones. But we have this shape here. So we fold it in half, and I see that if I fold it in half, then the tails on the sides are not going to match. But what if I fold it the other way? If I fold it horizontally, so hamburger and hot dog style. So if I fold it the other way, still same thing, it doesn't match, which means it does not have a line of symmetry. But if I take, for say, this diamond, and if I fold that diamond hot dog style, then my edges match up and there will be nothing hanging off. It's all overlapping itself. And if I fold it hamburger style, horizontally, then the same thing. So that does have a line of symmetry. Moving on to our next one, we would see that it does not have lines of symmetry, because if I folded it in half, then those tails again are going to stick out. So if it anytime that a shape, if it, at any angle, it doesn't, or it does, yes, if it doesn't overlap, then it's not going to have lines of symmetry. So for instance, even this triangle, it does have a line of symmetry because any way that I fold it, those corners, the edges are going to meet. And then this half circle here, it does, our rectangle does, our triangle does, and then our hexagon does as well. And like I said, a great in-class, you know, hands-on tool that we could do is, of course, having the students cut out their own shapes and folding them themselves and really, you know, getting that hands-on. So let's jump to the next question. So our next question is, we want to look at rotational symmetry. So what is rotational symmetry? So rotational symmetry is kind of like, you know, our question before, you know, if it, whenever we rotate it, does it still have the same symmetry as the original? So looking at the first shape, we're going to rotate each of these shapes 180 degrees. So remember we talked about before that that full circle is 360 degrees. But if I cut it in half, meaning we're only going to turn it halfway, not a full circle, halfway, then that's going to be 180 degrees. So taking a look at our first one, we're going to flip that 180 degrees. And we see that whenever we do, it does have rotational symmetry because it looks exactly like the first one. So we can put a check mark by that. That does have rotational symmetry. What about our diamond? So we flip it 180 degrees and I see that it still looks the same as the first one. So I would say that that as well does have rotational symmetry. What about the zigzags, this Z shape? I flip it 180 degrees and it does. So a lot of these are looking like they are going to have it. Now what about this triangle? Surely the triangle has rotational symmetry. It has 3 sides and 3 vertices or vertex corners. So let's flip it 180 degrees. Now, what I want to point out with this is that our arrows are now, the tops of our triangles are pointing in opposite directions, meaning the orange shape does not look like the blue shape, so it does not have rotational symmetry. Let's jump on to our next ones. So remember I talked about those circles. So the circles are going to be kind of easy give me ones, but we'll go ahead and do it just for fun. So let's turn that circle 180 degrees and we see that it does have rotational symmetry. And then we can jump over to our rectangle. It looks the same, so it of course does. What about our triangle? So we turn our triangle 180 degrees and it does not have rotational symmetry. And then as well as our hexagon. So our hexagon, we're going to turn it 180 degrees and I see that it does have rotational symmetry. So now we can talk about what a tessellation is. So a tessellation is going to be a repeated shape that goes on and on, you know, and it's the same repeated shape and it never crosses over one another and it never overlaps as, you know, either. So kind of a real life example. So my picture over here to the left is going to be bathroom tile. And so with that bathroom tile, you know, we could see it walking down our halls or even on the walls. Those blocks, you know, the cinder blocks on the wall or the tile on the floor, we'll see that they never overlap and they never, you know, cross each other, meaning that it's a tessellation. And then on the right side, I included a picture that I just found online, and it is of a student's work that they actually drew their own tessellations. So we see that in their, you know, work that they chose arrows, and those arrows, though they're different colors, they are still the same shape, and so they never overlap and they don't cross over one another, meaning that it's a tessellation. So I just wanted to include that because I think that it's a great resource that if we were in a classroom, that's something that we could do, you know, for the students to kind of have some wind down time and make their own tessellations. So with that in mind, a tessellation can be a vertex figure. So for this example, we were given an octagon, and the student was given three shapes, so the octagon, and then she was given a hexagon and this other shape. So she was asked to put them together, and then she was asked to take the shapes and put them one spot in between each. So what we're trying to determine, is this a tessellation or a vertex figure? Meaning, does it overlap? If it does overlap, then it's not. So what we're going to do is we're just going to go ahead and fill this out and see if it overlaps. So I see here that our shape begins to overlap some. So immediately I would know at this point that it's not, but for fun, we'll just keep on going. And it overlaps here. And then it overlaps here as well, and a little bit here. So I would say that this is not a vertex figure because it has that overlapping. So the answer would be no, it is not a vertex figure. And that's another fun example. In school, we always have those little blocks within the multicolored, and we could have the students make their own. And teamwork with their friends to see if they can make their own vertex figures. So for this next question, what we're going to do is we're going to demonstrate why angle QPT is congruent to angle SPT. So I see here, of course, my purple or pink triangle. That's going to be here, this one here. And I also wanted to stop and point out that these lines here mean that they're exactly the same. So this is congruent to this, and that is congruent to that. So I see, of course, my pink comes in, and then my blue comes in, and that is why that is true, because they are both equal. And then I can take a look at my angle QPT and angle SPT, and we're going to see why that is true. Because at this angle here and that angle there, it is the same shape, the same angle. So it is congruent, meaning it's the same. So then we're going to demonstrate why QPV in red and SPV are the same. So I see that those are the same, so that's true. And then for our last one, we're going to demonstrate why angle QVP is a right angle. So I want to stop right there, and I'm going to do my best to draw an angle. But I wanted to note that in math, this is not going to be perfect, but that's okay. So in math, whenever we of course, see an angle, we have a secret language, and that secret language is any time that there is a box in the middle of an angle right there, that means that we don't even have to use our protractor. We know, of course, that it is what's called a right angle, meaning a 90-degree angle. So there's no need to measure it or do any math behind it. We know for a fact, that's our secret code, that it is a 90-degree angle. So I could take this purple box here that I put, and I could put it in any of these corners here, and I would know that those are all right angles. So jumping to our next question, this is going to be a penta. And so if I was to take this penta, and I didn't make it perfect, but if I was to divide this into, of course, equal sections. So I did my best, but if we were to draw equal sections, we would see that there are 15 triangles here. So with that, we know we talked about that a circle is 360 degrees. So I'm trying to find here, and I kind of covered it up, but this O right here. So I'm trying to find what is the angle of N, Q, and O. Okay, so that's what we're trying to measure. So I know that my circle is 360 degrees. If I divide 360 by 15, because I can have 15 triangles, equal triangles here in my penta, then I would see that it is 24 degrees. So angle NOQ is equal to 24 degrees. And that's how we solve that. So for our next and final question, we are trying to measure, of course, the height of this mountain. So our student was given a 2-foot ruler. So she has this here in her hand, her 2-foot ruler. And what we would do is cross multiply. So we're going to cross multiply 2 feet by the height of the cliff and 1.5 inches apart by 1/4 or 1/4 of a mile away from the cliff. So I would just, like I said, cross multiply. So that would be the answer there. 1.5 inches divided by 12 inches is 0.125 feet. And 1/4 or 1/4 of a mile would equal, divided by 1 mile. I'm sorry, multiplied by 1 mile. Anytime we see of, we can just know that that is multiply. So 1/4 multiplied by 1 is 1 mile is 1,320 feet. So we're going to multiply those by each other. Anytime we see parentheses beside each other, we know that we are multiplying them. And that would give me 2h. So then I want to separate, of course, the h from the 2. So I would divide 2h by 2, and that's going to cross that out. And then I'm left with 165 divided by 2, which would equal the height of my mountain here is 82 feet. I'm sorry, 82.5 feet. And that would be the height. So that's all I have for us today, guys. I look forward to seeing you next time. Thank you.